A single wind turbine may be adequate for very local power users, but in many cases multiple wind turbines will be required to meet a larger total system demand for electric power. An array of multiple wind turbines is known as a wind farm, where farm is used in the sense that the wind turbines are harvesting power from the wind. There are economic advantages to having multiple wind turbines located close to each other, as opposed to a more distributed placement. The first advantage is shared infrastructure. Large components such as transformers, high voltage transmission lines, electrical grid ties, and other infrastructure may be shared if the wind turbines are close enough together. For example, essentially replacing multiple transformers with a single larger one. This is more cost effective. Second, operating and maintenance costs are reduced by having multiple wind turbines close together. A technician can service multiple units at the same site in much less time than having to travel to many different sites. Service customers pay for travel time. There are also some disadvantages associated with close placement of multiple wind turbines, in that adjacent turbines can interact. The wake from each turbine can influence the wind input to the others, resulting in performance degradation. The figure shows a side view with one wind turbine downstream of another, but recognize that the interference occurs laterally as well, as will be seen in the next slide. The green circle shows the normal wind speed profile upstream of the first wind turbine. The orange circle shows how the wind speed profile is affected by the rotor. The two dotted lines, orange lines here and here, mark the position of the rotor. You can see that the wind speed is substantially reduced here compared to the original wind profile over here by passing through the rotor. As you've learned in previous lectures, the wind has given up some energy to the rotor, resulting in this loss of speed. Downstream of the wind turbine, faster moving air from above, or the sides if we were looking down from the top, start to mix into the slower moving region as shown. At a considerable distance downstream, the second green circle shows that the wind speed profile in front of the second wind turbine here, the profile has nearly attained the original upstream profile. You can see from this illustration that it would not be a good idea to place a second wind turbine too close to the first wind turbine in the downstream direction, as the second wind turbine's output would be significantly reduced as a result of a reduced wind speed profile like the orange circled one shown. So, spacing between turbines is important for laying out a wind farm. In the lecture on what is the maximum power that can be produced from the wind, we saw that in the ideal case, the velocity downstream of a wind turbine was 1/3 the upstream wind speed V0. So, assuming that the wind speed behind the first rotor is 1/3 of the upstream wind speed, and using a momentum balance, Jensen developed a simple model to estimate the wind velocity behind a rotor, the equation shown here. So let's look at the layout on the right. At x equals 0, so this position here, we start with the upstream wind profile. So here's V0, and you can see that outside of the wake region, indicated by the thick black lines here, the wind has the wind speed V0. R here shown is the radius of the wind turbine rotor, so this plot is much magnified in scale. This is the rotor of the wind turbine, and so this is the plane where the wind turbine is sitting right here. And you can see that the wind speed arrows here are much reduced. They're 1/3 of the value of the arrows outside the wake region, so that's the ideal wind profile downstream of the rotor. The spread of the wake region downstream is calculated using the formula above there. If we go now to some position x downstream, the wind profile outside the wake region is still undisturbed. So you can see up here again V0, and you can see all these arrows then are undisturbed wind. Inside the wake region, you can see that the wind speed is reduced compared to V0, although increased compared to the 1/3 V0 value right behind the rotors. So the faster moving air has started to mix in as we go downstream to increase the speed of the wake region. So as it goes downstream, it picks up speed. The wake radius RW has a simple linear dependence on x as shown. We start with the wind turbine rotor itself, so at x equals 0, the wake region is essentially the radius, has essentially the diameter of the rotor right here is the wake region. And you can see that the radius of the wake down here then grows linearly with the coefficient alpha, which reflects the mixing properties. Using this simple model, we can estimate the size of the wake from a wind turbine rotor. The plot on the left shows how the centerline velocity varies with position downstream from the rotor plane. In order to make it applicable to rotors of all sizes, the downstream distance is normalized by the rotor diameter, so x over d here. And to make it applicable to all wind speeds, the centerline wind speed is normalized by the upstream wind speed v0. So we have v over v0 on the y-axis. You can see that there is a very substantial impact of the wake on wind speed for a considerable distance downstream. So a value of 1 represents an undisturbed wind speed. At 5 rotor diameters downstream, the wake value has recovered to about 83% of the upstream value. At 10 rotor diameters downstream, it's back to 92.5%. So for a very large 80-meter rotor, which is not unusual for current large wind turbines, 10 rotor diameters downstream is 800 meters, so we're approaching a kilometer downstream and still feeling the effects of the upstream wake. This is a really large spacing. The figure on the right shows the wake diameter, so I've plotted here diameter instead of the wake radius shown on the previous slide, RW, as a function of normalized distance downstream. You can see that at 10 rotor diameters downstream right here, the wake is spread to 3 rotor diameters in width. So this will clearly affect the lateral spacing of wind turbines. The plot on the left tells us something about the downstream spacing. The plot on the right tells us about the lateral spacing. We can use something called the array efficiency to characterize the influence of wake effects on the total output from a wind farm. So the array efficiency is equal to a numerator, which consists of the annual energy output of an array of wind turbines. So that's the actual output of the array. So that includes all the degradation of performance from the interference effects, whereas the denominator represents what would be possible if there were no interference effects. So we take the output of a single turbine at the site, the annual energy output of a single wind turbine, so that's at the site by itself without any other wind turbines around to influence its performance. So that characterizes the undisturbed flow. We multiply that by the total number of turbines, and that gives us our comparison. The table on the right contains some representative array efficiency values calculated using Jensen's simple wake model. The sketch on the left shows an array of 4 wind turbines, 2 in the front row facing the wind, so the blue arrow here represents the wind direction, and the second dimension is the distance between rows in the downstream direction. So if we look at some numbers in the table, let's start with just one row and 3D spacing along the row. So between the center lines of the 2 rotors, we have a distance equal to 3 times the rotor diameter. You can see the array efficiency is calculated to be 91% of what the 4 turbines would produce. The 2 turbines would produce if there was undisturbed wind. The last 2 rows of the table show the effect of downstream spacing. So along the row, the spacing is both 3D, Between the rows, if you have 7D spacing, 7 diameters downstream between the rows, we get 93% efficiency. If we decrease this distance to 5D, then we get a decreased efficiency of only 84%. So we can now take the numbers in that table or array efficiencies from another source or calculated and estimate the annual energy output of a wind farm. So it's equal to the annual energy output of a single wind turbine. Again, that's for a turbine with no others around it, so unaffected by interference from other wind turbines, times the number of wind turbines times the array efficiency. Just to remind you that the array efficiency values provided are calculated based on a very simplified analysis, so they're an approximation. Once you've installed the wind turbine with a particular spacing, you can't move them around. We know, however, that the wind direction can change. Our simple four wind turbine layout wind farm can illustrate this. So here's our 4 wind turbines, and suppose that the spacing between turbines was chosen for the wind direction shown. So we essentially have a wind here coming from the north. For example, let's suppose that the distance along rows was 3D as from the table previously and 7D downstream, and then we know this would give a very good performance array efficiency of 93% with a very compact layout. Now let's suppose that the wind direction shifts 45 degrees, so the wind is now coming from the northeast as shown here. The wind turbines are in the same location, but the nacelles and rotors have rotated to face the wind. You can see now the shifted angular position of the rotors in all the 4 wind turbines. But the support structure here, 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 and here have not moved. They're still in exactly the same place. But now because the wind has shifted, you can see that nothing lines up exactly anymore, and indeed the spacing between turbines has changed. All right, so in the distance downstream here, this is now somewhat larger than 7D, which is okay, good actually, but you can see that the lateral spacing has been reduced quite a bit. So if we started out with 3D originally, you can see that we're down to at least half that right now, which would have a very deleterious effect on the array efficiency compared to the case where the wind was blowing from the north. So you can see that it is important to take into account all possible wind directions when laying out the spacing between wind turbines for a wind farm. It may be that the wind direction probability for some directions is low enough that the array efficiency for that direction can be compromised without significant impact on the overall annual energy output, but in cases where the wind has a good probability of blowing from many directions, the lateral spacing between wind turbines will need to be much larger than the 3D spacing that gives us a good efficiency in the previous table. The bottom line is that local wind direction probability data must be taken into account in determining spacing. Let's conclude by summarizing. Wind farms offer an economic advantage due to shared infrastructure, reduced operating and maintenance costs per turbine. The array efficiency accounts for degraded performance arising from interactions between adjacent turbines. And finally, the wind farm annual energy output is equal to the annual energy output of a single wind turbine alone at the site, undisturbed by the presence of any other wind turbines, any interferences from other wind turbines, times the number of wind turbines, times the array efficiency. Please try the questions that follow to give you some practice with wind farm concepts.